Welcome to the AP Calculus BC video for skill number 230. I can solve population growth, half-life, and compounded interest problems requiring simple differential equations. The rather straightforward and obvious trivia question for the video is featured below is something, and the trivia question is, what is it and what is it used for? Alright, we'll start our notes on page 230A, and we're getting into some differential equations, and what makes a differential equation a differential equation is the fact that we're connecting the derivative of a function with the function itself. So one or more derivatives with the original function, and in this case we're going to have the most basic type of differential equation where we only have one derivative and one function. So we could also write this, if we were to divide both sides by p, we could write it like this, and we see that k can be considered our relative growth rate, and that's our constant. So the most basic way we probably have seen this in our life is, I add 10% to my savings account every year. And there you go. We have our constant of growth, our initial investment. So we'll look at some problems like that. This would be our change in, so dA dt. It should be noted that we're not restricted to the given variables. For example, you might see me writing dy dt equals ky, or dm dt equals km. Basically, the letter here is the function of interest. So we saw p, y, m, and I'll use a couple examples throughout our process. So with a differential equation, the only solutions of the differential equation that we listed here, the only solutions are the exponential functions y of t is equal to y of 0 e to the kt. And basically what we could say is y of 0 is our initial amount, and then y of t would be our amount after time t. I wrote it down here real quick, the definition of a differential equation, so that you can see it in words. Let's take a look at the next page. Okay, so right at the top I kind of wrote our general rule about differential equations that we talked about on the last page. You don't need to copy it, but I like to constantly go back to that. Let's take a look at example 1. Example 1 says, at time t equals 0, a bacteria population was approximately 256 million bacteria, I guess. 10 minutes later, the population had grown to 304 million. Create a model which predicts the growth, and what is the relative growth rate? Use the model to estimate the bacteria population after 30 minutes and after 90 minutes. So there we go again, writing our very general relationship between the differential equation and the solutions. So what we can do is we know at time 10 there was 304, and we know at time 0 there was 256 million. So we can use this equation to evaluate what k is. So we go down the process, I divide both sides by 256, then I take the natural log of both sides, and then I divide both sides by 10. This gives me my k value, which is my decay constant or growth constant, and in this case we're talking about growth. So we have a growth. We now have our model because we can plug our growth, our constant, into the model. And that's our relative growth rate. And if we're going to do it as percentages, we are going to move the decimal spot 2 points over. And our bacteria is growing at approximately 1.719% per minute. I would strongly encourage you, when you start to get these rounded numbers, to store them as variables on your calculator so that if you need to do calculations, you can recall the variable. So for example, I stored this under variable k using the store command, and then when I typed in the equation for the last step, what I did was I typed in 256e, and then I used my alpha key to type in k, and then I multiplied by 30. If you typed in the decimal, you'll get a slightly less than accurate answer. Do the same thing for the y of 90, and we get basically after 30 minutes there's 428 million, and after 90 minutes we have 1,202 million bacteria. This model probably has some constraints on it that are beyond the scope of this problem, but maybe if we had our bacteria in a petri dish, eventually they would start to fill up the petri dish too much, and there would be some limiting factors that prevented growth. So this model is only relatively accurate. In the future, we'll look at models which are more accurate. In 1986, Europe saw an atrocious disaster with the explosion of Chernobyl. And Chernobyl, when it exploded, spread radioactive material all across Europe, including cesium-137, which has a half-life of 30 years. How long would it take to decay to 1% of its initial level? So here we're not even given the initial amount, and we're interested in how long it's going to take until only 0.1% of its initial level is left. And we want to know what is the relative decay rate, or the rate of change. And finally, since the explosion occurred in 1986, what percentage of the radioactive material is still left in 2014? So we'll start this problem with our go-to, write out the differential equation, and see what we can do from there. As we scroll up, we're going to put I as the initial amount, since we don't know how much there initially was, or maybe we do, but I don't have it for this problem. Our initial amount is our y of 0, and then after 30 years, we have half of that initial amount. So if we divide both sides by I, we get 0.5 equals e to the 30k, and then we can take the natural log of both sides and divide by 30, solving for our decay constant. We get approximately negative 0.0231. If we translate that into a percentage, we have a relative rate of change of negative 2.31%. So that's our k value in percentage. They ask us how long will it take until only 0.1% remains, and so what we want to do is set up our problem with our initial amount, and we're trying to get to 0.1%, which is 0.001 of our initial amount. We can plug our decay constant, our rate of change, in for k, and then we're solving this function for t. And we find that for there to be only 0.1% left, it's going to take approximately 300 years of radioactive decay across Europe for most of that material to disappear. Quite a shocking amount of time. And they ask, the question said, how much is left in 2014, our current year? We can plug 28, because it's 28 years later, into the model, and we find that we get an answer of approximately 0.5236 which means 52% of the radioactive material that exploded from Chernobyl is still floating around in Europe. And that's 52% of the cesium radioactive material. There is also radioactive iodine, which has a shorter half-life of approximately 8 days. I think iodine. Anyway, so we've done a growth problem, we've done a decay problem, and now let's take a look at an compounded interest problem.
Hi! How are you? Do you want to see something freaky?
Alright, our final example, as always, writing out the general differential equation. Here's the differential equation, and if we have that, it implies that. This time our equation of interest I'm going to use the letter P for instead of Y. And you may recall that this looks very similar to our compounded interest problem, or interest formula, the PERT equation, as a lot of people refer to. So let's take a look at a differential equation problem with interest in mind. What we have here is the differential equation, and they tell us that our bank account is earning 7.1% on interest compounded continuously. So we could take our differential equation, and our change of principal would create an equation that looks like this. Our change of principal is 7.1% of our original principal. And we can convert, using this equation, we can create the implied equation, and we get the more familiar PERT form that we spoke of earlier, where you have the initial investment, you have the interest rate earning, and this spits out how much money you have in the account after so many years. So what is the amount in a bank account with 7.1% interest after 10 years if $3,000 was initially invested? Here's our general equation. We plug in 3,000 as our P of 0. We plug in 10 for T. And this is straightforward, just punching numbers into the calculator. And we find that after 10 years, at 7.1% interest, we have approximately $6,102. This looks quite familiar to those who know what I believe is called the rule of 72, which I'm not going to explain. But if you know that term, it probably supports that. Alright, that's the video. Thanks for watching. Alright, so the video is done, and the very simple trivia question is, featured below is a saddle, or a horse saddle, and it's used for horseback riding.